go over some of the results, some of the initial results and definitions here, and then I'll spend most of the time going through an example of a particular group which you may know seen before, which will illustrate some of the ideas. In the next few weeks, we'll return to the things that we skim over today, improving the details and investigating specific results. Okay, so what is a group? That's the first question we're asking. So a group in mathematics, well, begins with the definition of what a binary operation is. Now, we won't waste too much time or worry too much about defining this super formally. Take a hand out there. It's a binary operation. Well, the binary refers to two things. Remember, binary numbers are numbers made out of zeros and ones, two options. So anything that is binary is something which has two choices or two aspects to it. So a binary operation, well, you're quite familiar with these. You use them all the time. You use them from when you entered primary school and mathematics. So, for instance, you can write 2 plus 3 equals whatever it is, 5. Right? So it's a binary operation. It's an operation plus which takes two inputs. Okay? Or you can write 3 times 7 equals 21. This is another example of a binary operation. An operation on certain kinds of elements that takes two elements, gives you a third. So a binary operation, let's say a binary operation on a set S is an operation taking two elements. Let's say S1, S2 from S and reducing a third element. They happen to be one of S1 and S2. Not claiming it's a new third element, so most of the time well, now it's traditional when you're not talking about any particular operation. You're talking about a particular well-known operation. You use the equivalent symbol plus for adding numbers, multiplication or multiplying things and so on. If you're just talking about an operation abstract, it's traditional to use an asterisk for the operation. So this is the third element. So here I've got an operation which is denoted by an asterisk. I'm not saying exactly what operation it is. I'm not saying exactly what set S is. I'm only writing this down just to give definition to the idea and concept of what a binary operation is. So particular examples are addition on the integers, say, multiplication on the integers, plus on the integers, multiplication on integers, many, many more. What binary operations are. And when you start to think about it, you're already familiar with a whole host of these. Okay? Addition and multiplication of numbers are the ones that spring most immediately to mind. And you could say these come in many different forms because they come as operations on many different sets. Natural numbers, integers, rationals, real numbers, complex numbers. So, strictly because we're saying a binary operation, it's an operation on a set S. So if you have different sets, you're speaking formulas. But you're also aware of these in lots of other situations. Even vectors in your linear algebra groups. And in linear algebra, you studied how you have this idea of adding vectors together. You take two vectors, you add them together, you get a third vector. It's a binary operation on a certain set of vectors. studied matrices. You studied at least two binary operations on matrices. Add matrices together. They come from a set of matrices of the same size, the same dimensions, so it makes sense. You can add a pair of matrices together to get a new matrix of the same size. And that's again binary operation. If you look at a certain set of square matrices of a certain size, so all 3 by 3 square matrices, you can multiply them together. 2 3 by 2 matrices, multiply them together, you get a new 3 by 3 matrix. It's again binary operation. So you're already familiar with a whole host of things. Even more, we studied functions, so real value functions. If you have a certain set of real value functions, any operations you do, you can add two functions together, you can multiply functions together. You can, this is a very important one, it's a very deep one which occurs lots and lots of times. Compose operations. Run one operation after another, providing they line up in suitable ways. One function are actually. So take a pair of functions and under suitable conditions you can compose them to produce a new composition. So that's a very, very important example of a binary operation that occurs in a whole host of different areas. Multiplication of matrices can be viewed as an operation. Multiplication of matrices is kind of an example of composing operations because we've done linear transformations in linear algebra. No? Okay. Well, I think towards the end of the linear algebra course, and certainly all through next year in the linear algebra, you need the idea that matrices are naturally associated with certain functions. Matrices represent functions. And what you're doing when you multiply matrices together really is you're composing functions that represent them. So matrix multiplication kind of fits into that type of composing operations. So in this introductory paragraph, it just zips through mentions, cites, and locals. So what that means is you have this basic concept of a binary operation occurring in lots of different areas, lots of different functions, sets of numbers, sets of functions, sets of numbers, sets of vectors. It's a common idea of a binary operation. So there's this subject in mathematics called abstract algebra, or more particularly the group. So the group is very simple. It's a definition 5.1. Group is just a set with a binary operation. So what group theory is it, since we have this idea of a binary operation occurring in loads of different areas, group theory says, well, what can we deduce if we study the idea of having a binary operation without looking at the particularities of the numbers, particularities of the vectors, or examining exactly what kind of functions it's composing. Just look at the idea of having a set, having a binary operation. What can you know? What kind of structure can you see, or what kind of facts can you deduce about binary operations? So that's what if you just want to go down and get a handout. That's what group theory does, sets out to. And it's a large part of mathematics. It fits inside the more wider subject called abstract algebra. So abstract algebra has other fancy things in it, parts of the groups, rings and fields. Rings and fields are sets with two operations. Okay, well let's look at the definition of group. So group isn't just set with any old binary operation. We do assume that binary operation has certain minimal nice properties. So these are set out here in these four axioms. So in order to qualify as a group, set of the operation has to be these four back and examine detail. First of all, so here, the group is called G. The operation, as they traditionally are, it's talking about operation, the abstract. The operations represented with asterisks. Think of the asterisks as being an operation like plus. Put it in between two elements. So A star B, I tend to call it star B. A star B represents the third element, represents the S3. First property is closure. So what we say is that in order to be called a group, the operation must have this property. The new element that it produces must be in the set as well. And that's certainly the case for addition of integers, multiplication of integers. So it isn't the case that the operation will bring outside this. Say that the set, so this word closed, the set is closed with respect to the operation. Doing the operation on elements of the set always keeps you inside the set. Third, the second property is associativity. That is term associative. We have addition of vectors, it's a general concept that we discuss. Associative means if you've got this triple property, A star B star C, because it's a binary operation can only work by taking two inputs, X star and Y, two inputs and giving you the output. So if you've got a list of three elements, A, B, and C, you want to multiply them together, like that, A star B star C. Well, there's two different ways you could evaluate it. You could evaluate B star C first. There's a handout down here. You could evaluate the A star B first, which is the order indicated here on the right. Evaluate A star B, and then whatever element that is, star of C. But the other way you can do it is evaluate B star C first, and then evaluate A star. So whatever B star C. And being associative says that whatever way you do it, you'll always get the same answer. So it's a nice property. It indicates that the operation is well. Certainly, addition of any kind of numbers that we're used to seeing, multiplication of numbers, real numbers or complex numbers is and it's in the third and fourth property that kind of the group theory really gets going, that you get some kind of nice properties of the operations that leads to. The third property is the existence of an identity. This is a special element in the operation. It's very, very special because when you multiply it by any other element A, E star A, or indeed A star E, in that order, you always get back the other element. It's very special. It kind of has no effect when you operate on another element. Does addition of integers or numbers have an effect? Add one to something. One is the identity for multiplication. Zero is the identity for addition. You take any number, you add zero to it, it leaves the other number unchanged. It's still whatever it was. You take any number and multiply it by 1, it's still the same number. Multiplying it by 1 is the same. So 0 for addition and 1 for multiplication are the identity elements. And when you think about addition of matrices, what's the identity element for addition of matrices of certain size? size 0. So when you add that matrix of zeros to the other matrix, it's going to leave the other matrix. For multiplication of square matrices of a certain size, the identity element is the identity. Multiply other matrices by that matrix. So there's this idea that in a group, the group has to have an identity. The fourth axiom is the existence of inverse elements. This refers to the special identity element introduced in axiom 3. It says every element of the group has to have an inverse. Now, the inverse element, given an element A in the group, the inverse element is that special element such that when you multiply by A, operates on A, is the special element, you get back the identity element. So, what's the inverse element, say, for the element minus 2? What's its additive? Minus 2. Which element do you add to minus 2 to recover the identity? The identity element for addition is 0, remember? So, the inverse element for 0, 2 was minus 2 plus 2. And if you think about it, every integer has an inverse with respect to addition. So to use the term negative. Is there an inverse for 2 in the system of the integers under multiplication? Is there an inverse? Well, that's the right idea. Half is floating around, but it doesn't qualify as an inverse in really sense, because you see, crucially, we want the group to contain. There has to exist this inverse element set. Now, half, of course, is not an integer. If a half was in here, multiplied by 2, yeah, you can get that again. Crucially here, Z does not contain this. Does not contain the object, which should be inverse element 2. So this shows you why. So this shows you why Z under multiplication is not equal. It's a negative example. Z under plus is a Z under addition. Z under multiplication is not. Now that's not to say that there aren't groups with respect to the operation of multiplication numbers. If you take the rational numbers, the rational numbers gets around this problem of half number. The rationals, all the inverses are present, except all but one case. In order to be a group, the rationals under multiplication, I have to do something to the rationals first. It's just one single problem to do with axiom 4. We're talking about the rationals. Have to exclude 0. Yeah? Because this axiom 4 works out fine for every. Take the A at the beginning. It says for all A in sections, so for all A in the rationals, it has to exist in multiplicative numbers. Identity element is 1. So for every rational number, in order to be a group, there would have to be another rational number, so we multiplied it by the first one we got back. And that works out fine for every rational number, but except for 2. So there ain't anything that multiplied by 0. So we have to exclude a single element, exclude 0 from it. Just look at the non-zero rational. The non-zero rational numbers do the operation of multiplication. So those are the group axioms. That's the minimal structure or the minimal properties that we ask for in order to name the system. The system, which is a set, and the operation that goes around it, which is a pair of set and operation. That's the minimal set of properties that we require in order to call that group. And then group theory, in a single sentence of what is group theory? Group theory is just studying what are the consequences of these axioms. When you look at them 24, they seem fairly straightforward. You recognize them, you recognize what they're talking about, that's the analysis. But it turns out that, first of all, there are lots and lots of different examples. You see systems like this. We've already talked about numbers of addition. Systems like this occur all over the place. There's lots of them. So that indicates that it's present. And secondly, when you start looking at the consequences, you see that there's a huge amount of structure, an awful number of different groups. So, different groups. Well, when we get into it, we'll see the concept of groups being equivalent. Isomorphic is the technical. Groups are equivalent means that really, although one might be a group of numbers and there's some operation, the other one might be makes some operations. Although they look like they're composed of different objects, as groups they behave exactly the same way. So the mapping between them preserves all the structure. It says that. Well, even after introducing this idea that groups which occur in different areas are in fact the same group, there's still an infinite number of different possible groups. So, slides, certain slides. So, group theory is really just working out all of the consequences of these four axioms. So, it's impressive that there's a huge rich structure of mathematics still presents problems today, unsolved. It all just starts in these four axioms. But these four axioms are enough to certainly. These four axioms are satisfied by the integers under addition, and if you just concern yourself with the integers under addition and work quickly with multiplication, then you've got number systems, and you've got prime numbers, and well aware there's lots of problems around this. Okay, so this is what a group is. So probably you've never seen that before. You've never heard that word. But even if you're seeing that for the first time, you're already quite familiar with the concepts. So you're seeing them all the time in numbers in school, vectors now in your algebra, matrices. You see these concepts. You recognize what's being told about there. Okay. Now, with the time remaining this morning, I'd like to show you. I'm going to take one specific group and just introduce you to it and just look at it. First of all, it's got a name. It's called the dihedral group. Dihedral group D3 of order 6. Order means size or number of elements. Okay, you might recognize what it is. The yet, but it's not something wholly unfamiliar to you. You can start to describe what it actually is. So it's a set. It's got 6 things in it. It's got 6 elements in it. And there's something about the number 3. Well, this is the set of symmetries of a regular triangle. The regular triangle means all 3 sides are the same. The regular triangle. Now, what's the operation? Remember, for a group, I have to tell you what the set is and what the operation is. I can't just say the group is a set, unless the operation is the operation is composition of symmetries. So, what are we talking about here? Well, let's draw a regular triangle. Good enough. There's a regular triangle. What kinds of symmetries does it have? Well, the symmetries come in 2 flavors. The symmetries that it has are various types of rotations, various types of reflections. You'll think that the triangle is being centered at the origin, centered at the origin. What do we mean by symmetry? Symmetry is an operation, a geometric operation, either a rotation or reflection, that you do to the triangle keeps the triangle looking the same. So what kind of a rotation do you do to it? Leave the end picture still the same triangle. And what are you going to rotate? Just these words. Well, see, if I rotate it by that much, it looks the same. Well, it looks different if it's irregular. Imagine it to be a regular one. That's the same triangle. How much did I rotate it by? Quantify it that way. Or a third of a full turn. Yeah. 2 pi over 3 radians. So when you do that to a triangle, it still looks the same. Or you can rotate it by 2/3 of a full turn, which is that. Or indeed, you can rotate it by 360 degrees. Because I could have saved myself a bit of hassle, just rotated it by 0. It's the same thing. Same thing in terms of it's the same effect. Rotate it by 0. So there seems to be 3 rotations. 3 rotational symmetries. E R1, R2. So E is going to be rotation by 0. I'll work in terms of radians. R1 is going to rotate by 2 pi over 3 radians. R2 is going to be rotation by 4 pi. And as is usual, all these rotations take place anti-clockwise. That's the default direction. Are there any other rotational symmetries that it has? Are these all of the rotational symmetries that it has? Is there any other rotation you can do to this that leaves it unchanged? Which isn't equivalent to one of these. I could rotate it 10 times. That's equivalent to. These are the only three. Each rotation is different to the others. They make the triangle look the same, but they're different rotations. Now, what kind of reflections does it have? Well, a reflection of the plane is you have to have a line, and you reflect the plane and the line by sending every point perpendicularly through the line out to its mirror point, image point on the other side. So there are three axes of symmetry, three reflection axes in this triangle. If you reflect the plane in any of those three lines, the triangle ends up the same. Let's see if I can do it here. It's difficult to do a reflection of the plane in a drawing like this. If you turn it upside down, if you think about it, that's the same thing. Kind of. It's very suspected. So, there's a triangle. It's the same triangle you were looking at a minute. I just reflected it in that glass. This vertex up here is still in the same position, still up at the top. The other two have swapped. This one is on the left. Now, if you're looking at it, you reflect it. You can reflect it in the other axis as well. I can reflect it like this. So that kept this vertex down here. Just see reflected my triangle drawing skills aren't very good. Now, traditionally, reflections are denoted by the letter S. So I'm going to label these S1. Let's go around anti-clockwise, S2, and S3. Three reflections, S1, S2, S3. So S1 needs reflection in that vertical axis. So these are reflections in the lines shown. The axes of reflection. There aren't any other reflection solutions. Those are all. So these are my 6 elements. R1, R2, S1, S2, S3. Each of these symmetries is a function from the plane to the plane. What I'm doing is I'm rotating the plane, literally rotating the sheet plane. The sheet plane in particular is the plane, so I'm rotating it. And I'm reflecting it, sending every point to partner points on the other side of the axis of deflection and so on. So each of these symmetries is a function from the plane to itself. So they can be opposed together. Now, composition is going to be the binary operation. Set of systems. This shows another abstract nature of what we're doing. We're not talking about numbers. We're We're not talking about the points. Those aren't the elements. Elements of the group are these six functions. Six functions. Those are the objects. The operation we're doing, composition, is an operation on those functions. And the key observation here is these are symmetries of the triangle. You do any of these six things to the triangle still looks the same. If I rotate it about the origin, it's still looking at still looking at the same triangle. So triangle sitting in front of your eyes. Now that observation is key because what happens if you compose two symmetries? Well, if you do the first symmetry, still the triangle. You do another symmetry, if I do a reflection in the vertical axis now, but it's still going to be the same triangle. So if you think about the combined effect of composing the two symmetries together, start off with a triangle, compose the two symmetries, still looking at the same triangle. So the composition is a symmetry as well. Key observation. And it's by definition, composition of symmetries. Take two symmetries, that's the binary operation, compose them, from one symmetry after the other. Composition of symmetries is again a symmetry. So D3 that I've introduced here, dihedral group 3 of order 6, D3 consists of these three functions. If I compose them, take any two of them, compose them, I must get one of six. Our investigations or explanations has kind of persuaded us that these are all symmetries. If I take two of them and compose them, I must get one of the others. This observation is you compose two symmetries, you get the other symmetry. So taking any pair A, B from D3 consists of 6 things. If I take any pair of them, so we call them A and B, must be that A, I'll use the little circle, remember that's the symbol we use for composition functions, must be that A after B is again in to see the effect of all these compositions. It's a neat way which works well for groups of small order, small enough so that it will fit the page. You can do out what's called the Cayley table. Cayley table, Cayley, but you can also call them a multiplication table, operation table for the group. What you do is it's a table, it's like a matrix, label the rows and columns with the group elements. Conventional to start with the identity. And you should probably, well, you don't strictly have to, but you should probably use the same ordering of the elements. Column labels and row labels. What am I going to put in this position here? I'm going to put the result of composing R2 with R2. Over here, I'm going to put the result of composing S1 with R1. Now, I have to be careful. I have to describe clearly what I'm doing here. Remember, we would have discussed this when we introduced composition of functions in chapter 3. Composition is not mutative. not the same as B composed with A. In certain special circumstances, certain special setups, can be. You should really expect those two unless there's special reasons. So we have to agree that inside our table, it's the same convention you have for naming the entries of matrices. In a table, when you see an A here, B over here, the element you put at the intersection is A composed with B. So the row index goes on the left, the column index goes on the right. It's the convention which we use for drawing. It's just a convention. You could equally well do it by putting B on the left and A on the right, or you could be doing it the opposite way, which last time. We need this kind of convention so that we can all read it. It's the same convention you use when you're naming entries of matrices. Now, I'm kind of running out of time here. Now, of course, we can fill in some of the entries straight away because if I compose one of my operations with the identity operation, that's the rotation by 0 radians. It's just not doing anything. If you compose that with any of the other operations, clearly just has the effect. You do the operation, then you do nothing. Or compose it the other way, you do nothing, then you do the operation. Still has to do this. Now, running out of time, so I'll just do one interesting one, and then I'll leave you to complete the table as an exercise. Let's think about what entry is going to go here. S1 composed with R1. What is S1 composed with R1? It must be one of the 6 symmetries. You do a symmetry, the triangle is unchanged. It's the same triangle. You do another symmetry, the triangle is unchanged. So the overall effect of composing them should be the same triangle. How can we work out which of the 6 it is? Well, there's a neat little method to do it. You can do it by naming, you label the vertices. Just track how the vertices move around. Now in this composition, you do R1 first. Do the rotation R1 first. So of course that moves the vertices around like this. R1, remember, was rotation by a third of a turn anti-clockwise. You then do S1. Now let's be careful. What was S1? S1 was reflection of the vertical axis. The axis doesn't still have to. S1 is an operation on the plane. So it's reflection of this vertical axis. You still have to reflect the triangle, this vertical axis. Performing S1 needs 3 up here, and it swaps 2 with 1. Of course, the composition is this. The single operation in front of the start and the end. Which symmetry is that? If you look at what it does to the vertices, you should recognize which of the 6 we introduced at the start, which of it is. Anybody see what it was? It's S2, isn't it? It's S2, reflection in this axis. That's the one which leaves vertex. If you start off here, it's going to leave vertex 2 fixed, because that's just sitting on the place. But vertices 1 and 3 get flipped over, as they are here. So yeah, that's S2. Good. When you compose S1 with R1 in this way, you get S2. So S2 is the element. So set an exercise there for your tutorials is to complete this table. What's R? Well, here's a quick question. What's R1 after S1? We'll turn out that has to be the other reflection. Not S2, not the one we got here, but S3. To show this, so completing the table means for every entry in here, you're going to want to put one of the six symmetries. So that's our first look at one of these dihedral groups. Obviously, you can do the same thing for any regular special outline. Dihedral group, square, pentagon, hexagon, septagon. We'll consider some of the other ones, I think. Okay, we'll leave it there for this morning, so we'll continue with this next week. Now, I don't think much of the exercises in the notes are opened up to you at the moment, but work on completing that table as a good exercise, get familiar with the idea of